All right, so today's lesson is about inductive and deductive reasoning. And so inductive, if you read the definition, it says the process of reaching a concluding statement based upon a pattern of examples. And that will help you get to a conclusion. So you kind of do that when you walk on Olathe South. You look at people and you're like, oh, what do you notice? And then as a result of what you see or the different examples that you look at, you can make a conjecture. Okay, and so we're going to be talking about those types of things. Look at a pattern, look at your examples to see what you notice. And we can make a conjecture based on what you see. Okay. And so one thing you would say is like, oh, I noticed that so many people at South wear t-shirts. And that's pretty true. If you look around, you're like, a lot of people have a t-shirt on, don't they? But if you make a conjecture, it may not be 100% true. Okay. So if you're like, no, it really isn't true, you can come up with a counterexample saying, no, look at this person right over here. They have, instead of a t-shirt, they've got a tank top, or they've got a shirt with a collar, or something like a sweater on today. So a counterexample kind of says, no, not really. Okay. And you can give a counterexample by using words. You can use like an example, or you can do a drawing. But those would be like to say, no, it's really not true. Now, you can't really prove an inductive reasoning by giving a huge list, because there's so much more that you haven't seen yet. But one way to show that something is true is to use deductive reasoning. Okay, you can make a proof, or you can show based upon facts, rules, or definitions, or properties that something is a logical conclusion. So inductive is looking at examples to come up with a conclusion. But in deductive reasoning, you have something a little bit more formal. So let's look at this. And so if you're based upon facts, rules, definitions, and properties, including something called the law of detachment, this P and then an arrow to Q actually can be read if P then Q. Okay, so let's look at this. Oh, I did not mean to cross that out, but P then Q. So it means if P is Q, well, then Q has to be true as well. Okay. And so here's an example. If your car is out of gas, well, then what follows is then your car won't start. And so that is a fact, rule, et cetera, where like, hey, if this is the case, then that will be the result. And so if your car's out of gas, then it won't start. So, all right, here you go, wise one. Your car is out of gas. Well, what's my conclusion? Well, my car won't start. And that's an example of deductive reasoning, because it has to do with, if this is true, then this other thing has to follow as a result. We use this in geometry, be like, oh, if you have a triangle, well, then we know we have three sides. Oh, if we have a triangle, then we know as a result you have 180 degrees on the inside of your triangle. And so there's certain things that are like, if I have this, well, then this is true. And we'll use deductive reasoning when we do proofs later in the chapter. And so today we're going to focus on inductive, but I wanted to kind of spread out the tarp to say, hey, this is what we're doing in this chapter. So a statement, you can make statements. I do it all the time. Like, everybody in my classes are all 6 foot tall. You're like, yeah, that's not so true. So a statement may be true, it may be false. So you can make lots of statements, and they might be true and they might not be true. And so we assign a truth value, or we can say, hey, that is not true, or that is true, to any statement that we see. Okay. And then beyond that, again, we're working through some vocabulary. There's such a thing as and or. Okay, so a compound break on your body is when you not only have a broken bone, but also it's sticking out of your arm. And so that's what I believe to be true. So a compound statement is multiple things put together. Okay, and they may be and they may be or. So let's check this out. An and type of problem would be here. And there's a shortcut. Oh, shoot, I meant to highlight. Here we go. And has this little notch, okay, upside down V, and that's a shortcut way. So again, math people like to be able to say, okay, we've got a compound statement, and between the two things, I want both to be true. Okay, so an and symbol means both things have to be true for the statement to be true. So an example would be, to have a square, what do you need? You need 4 congruent sides, and you need 4 right angles. Okay, so if you just have one of them, if you have 4 right angles, you may not have a square, you may have a rectangle. And so, but to have a square, you need 4 congruent sides and 4 right angles. And so that's going to be a compound statement that you need one and the other. Like you need both of them to have a square. The or, however, you could do one or the other, and that's a V, okay, an or. That means one of them has to be true for the statement to be true. More than one could be, but at least one needs to be true. So to attend South, you could be a student or you could be an employee. Those are options. Could you be both? I don't know. I don't know if they pay students on the slide, but anyway, to be at South on a regular basis, you could be a student or you could be an employee. You don't have to be both. You could be both, maybe. If that is the way it is. So, okay. The next thing is we're going to apply inductive reasoning. Where again, look at the top. Inductive reasoning means that you look at a series of examples and you're like, okay, can I make a conjecture about what I see? Okay, can you see those patterns? Can you look at those examples? So if we look below here, you'll notice there's a series of numbers 8, 9, 30, 10, or 11, and then 12, 30. You're like, oh, I noticed that every time you look at these, there's a pattern. Okay, you're looking at these examples. What do you notice? Well, every time they are going from one to the next time, you're adding an hour and a half. Okay. And so what is your conjecture? We have to always talk about where you start. So that somebody walking in the room, if they just saw your words, they could actually recreate the cycle as long as they wanted to. So you'd say, okay, starting at 8 a.m. And then you would say, the next time is 1.5 hours or an hour and a half, 1 hour, 30 minutes later. So you start at 8 a.m. Okay, that's what it says. I got to read it out loud because you can't read my writing very well when I use this pen. But starting at 8 a.m., the next time is 1 hour and 30 minutes later. So from 8 to 9:30, then 9:30 to 11, and then 11 to 12:30. And so what would be the next term? Well, the next item would be 2 p.m. So following that procedure. Okay, look at those stars. Again, here is a sequence of things. Okay, we've got examples and we look for a pattern. That's step 2. And then we can make a conjecture about what describes the pattern and then apply it, okay, to give you the next term. So those are kind of the steps for using inductive reasoning on patterns. So there's a star and it appears to be spinning. Okay. And so we're like, okay, what would be my next star? If you look at this, you can tell the best star drawer. So it kind of looks like it's not terrible. It'll be right here. Okay. So, oopsie. That should be up here, shouldn't it? And so our conjecture is this. Start with what? With a star with shaded top. Okay, you see how the top is shaded? And then the next star's shading is, or rotates, okay, counterclockwise. And you could even be more precise and like counterclockwise, and you could talk about how many degrees that would be. Okay, the last one in this set shows you more numbers and says, okay, 150, 25. Okay, can you tell this divided by 2? Okay, each term is half of the previous term. And so what's a conjecture? Start with 100, divide by 2 each term. That's a D. Divide by 2. Make next term. Okay, so you divide by 2 to get to the next term. So what would it be to get to the very next item? Well, you divide the last term you see by 2 and you get 3.125. So the next one here would be 3.125. Okay, so again, inductive reasoning, look at the pattern, summarize what it is, start with this and tell what you would do to get from one term to the next, and then you can provide the last term. And so if I give you a situation, you can look and say, hey, what was the conjecture if you talk about taking the sum of an odd and an even number together? Like, I don't know what that is. Well, on your homework, you're going to see things where, like, okay, take a square and find its perimeter, and then double the length of each side of the square, and then see what happens to the perimeter. Well, do it. Like, pick a square and pick like the side length to be like 3, okay, and then find the perimeter. And then double it to make the side length to be 6, and then see what happens to the perimeter. So they may not give you specifics, but they give you directions so that you can apply it and see, oh, I can create my own examples to see what's happening. And so the sum of an odd number and an even number, well, try it. Take an odd number plus an even number. So you could do like, I don't know, 5 plus 6. Okay. Oh, I get 11. Okay. All right. Try it again. Try 2 plus 3. Okay, that's 5. Oh, I've noticed that as I add an odd and even number together, I'm getting an odd number. So what could you say is your conjecture? The sum of an odd and even number is odd. Okay, so absolutely you can say that. And they're like, okay, that was really fun. So try the product of 2 odd numbers. Okay, well, let's try it. 3 times 5. Okay, remember product means times. All right. How about 5 times 7? All right, that's 35. Okay, it looks like when you multiply 2 odd numbers together, you also get an odd number. So the product of 2 odd numbers is odd. Okay. And the thing is, you're trying a couple and you're not proving it, but you're just saying, hey, I've noticed that. That's my conjecture. And someone could come along and be like, nah, look at this one. Okay. So there can be a counterexample for certain problems where they're like, I found a hole in your thoughts. Okay. So just because you make a conjecture doesn't mean that it's full bulletproof. However, that's kind of what we're going to say. Hey, make a conjecture. Okay. And so if you look at the next 2 questions that we have here, they're going to say, hey, are these true or false? And if they're false, can you give a counterexample to prove it wrong? So like if I'm like, oh, everyone in my class is 6 foot tall. We're like, let's measure this kid. This kid's only 4'8". And you're like, oh, okay. So that's a counterexample to disprove your statement that says everybody does this. Okay. Or this is my thought or my conjecture. Okay, so let's check out these conjectures. Okay, are they true or false? Okay, complementary angles have a sum of 180 degrees. You're like, complementary don't. That's a lie. Okay, complementary means they add to be 90 degrees, so that would be false. Okay, so what your job to do would be to say, okay, well, that's false. Okay, and so why? Okay, so you give a counterexample. So you write counterexample. Can't spell example. And the counterexample is, all right, if I have a 60-degree angle and I have a 30-degree angle, okay, and I call them like angle B, A and B. So angle A and angle B are complementary and don't add up to be 180 degrees, okay? In fact, they quite add to be 90. So complementary, no, that is not even true. Look at this counterexample. You're like, everybody, at South, wears red or gray. I'm like, look at this kid. No, he doesn't have red on today. So, all right, how about this one? Multiplying 2 times any number makes the product even. So if I take 2 times a number, do I get an even number? And so you're like, let me try it. Let's get some examples. So example, okay. 2 times 5. Well, that's even. Okay, 3 times 2. Okay, that's 6. Okay, basically, if you take 2 times any number, you do get an even number. So that's true. Okay. And then the last one, non-collinear, like, oh, for the love. Well, on your homework, you're going to have questions where you're like, you've got to look back at your notes. There's one about supplementary and talking about, do they make a line? Well, go back to your Unit 1 notes and say, what do we know about supplementary angles? Also about 2 points, do they make a line? So you've got to kind of look at those concepts. So non-collinear points must lie on the same line. That's not true, is it? Okay. Non-collinear by definition means they're not collinear. Okay. So this is a counterexample. Okay. The counterexample is this. If you've got 2 points on the line, you got C, so they're not collinear points. Well, notice points A, B, and C. Okay, points A, B, and C are non-collinear. Okay, so are non-collinear and don't lie in the same line. So basically, you disprove it. You're like, no, look at this. Okay, and so on your homework, they're going to ask you to look at 3 lines. They're like, oh, do 3 lines always intersect at one point? And the answer is no. Of course not. How can you draw 3 point lines that don't cross at one common point? No. Oh, absolutely. I mean, you can graph 2 lines and have a third line, they don't cross at a common single point. Okay, here's an example of them crossing at a single point ish. Okay, but the one on the left, yeah, that's an example, counterexample. Say no. Just because you have 3 lines that cross doesn't mean they cross all at a very single point. So there are points of intersection, but they don't have a common where all 3 cross. Okay, so the next one for Amy talks about, she at week 1, she had 5 NHIs, okay, week, and then NHIs. And week 2, she had 8, okay. Week 3, there were 12, okay. Week 4, there were 17. Week 5, okay, if you follow the pattern, you can kind of see what's going on here. Week 5 is going to be 23. Week 6 is going to be 30. 7 is 38. And week 8 is 47. How did I get those last things? Well, notice, how did you get from one point to the next? Well, this one, you plus 3. How did you get from here? You plus 4. How did you get here? Well, you plus 5. Plus 6, plus 7, plus 8, plus 9. And so that's how you get that. So in week 8, she had 47 NHIs. Okay, so you kind of have to look to say, hey, based on the sample you gave me, can I see the pattern? Can I make a conclusion? Okay, can I talk about a conjecture? And then can I try it? Okay, Venn diagrams. In class, I had people make a Venn diagram about pets. Okay, and it was pretty cute. Because we talked about stand up if you have a cat, and I had people stand up if they had a cat. And I said, stand up if you had a dog. Okay. And we counted them. It was kind of like this. I think this was it. There were 17 people with a dog, and there were maybe, I don't know, 8 people with a cat. Okay. Well, the thing is this, how do we put that in the Venn diagram? Again, we use a Venn diagram to help visualize what is going on and who is in what group, okay? Well, I said, well, you know what, stand up if you have both. And there were about 6 people who had both. So we put this right here because that means I'm a member of the cat circle and the dog circle. Now, what do I do with this blue dog circle? Okay, do I put a 17 right here? And the answer is no. If you add up everybody in this dog circle, you should get 17. Okay, so that means there's going to be 11 people who only have a dog. There are 6 people who have a dog and a cat, and then that means there are 2 people who have a cat. Okay, and so again, in the cat circle there are 8 people. In the dog circle there are 17, but there are some where they overlap. Okay, and so you can't directly just add 17 plus 8 to get 25. Really, truly, the people in the room who have pets are 19. Okay, so if you just add these guys together, you will double count some people. Okay, and so you got to be careful to be like, all right, how am I figuring this out? So he's like, okay, what about the people who have a dog? Okay, dog is equal to 17. What do people about to have a cat? Okay, that's 8. What about a dog and a cat? Okay, remember, and is the look on the front side of your sheet, dog and cat. Well, there were 6. Okay, what about a dog or a cat? Okay, that's everybody combined. That's going to be 19 people. Okay, And so a dog or a cat, well, if I had everybody stand up, they're like those who have just a dog, those who have both, and those who just have a cat, every single one of those 19 people would stand up at that point. Okay. So, and or are different, aren't they? And so if you look down below here, you can see that, how many students are enrolled in all three classes. I mean, all of them at the same time. Okay. So this would be here. Okay. The people in this group are enrolled in jazz, tap, and ballet. Just like here in the middle, these people have both a dog and a cat. They're members of both circles. They're members of the cat mama club and the papa, or the dog owners club. Okay. And so here they're members of each circle. So there are 9 students who have both. Okay. How many students have jazz and ballet? Okay. Well, jazz and ballet would be right here. And some of those kids have tap, jazz, and ballet. Well, these guys just have jazz and ballet. They're like, that's plenty. So the people who are members of both these circles, 9 plus 25 would be 34 people who have jazz and ballet. Okay. And then the last one is going to be, okay, so those who enrolled in tap or ballet. Well, everybody here is enrolled in tap, right? And then everyone here is enrolled in ballet. Okay, this whole circle here. So if you add up everybody who's either tap, no, some of them might have lots of other classes. Some of the people also probably have pets, but that's not what we're talking about. So what we want to just exclude would be the people who are in jazz. So you want to find the total number of people in all the classes, you just add up these numbers, and there would be different subgroups of this. But if you add up all these numbers, you should get 121 students. Okay, and you should label these as students. I'm just using a Sharpie, so I'm not writing the notes. Okay, the last topic we spoke about was, hey, are we using inductive or deductive reasoning? If you look at the front, you'll remember inductive reasoning is you look at examples and you try to make a conjecture about what would be true, okay, based on the examples that you see. So again, if you're walking around school, you're like, hey, I noticed this about the kids at South. I noticed this about the teachers at South, or whatever. And so I can't really prove it, but you can disprove it. You're like, hey, I noticed a counterexample. But let's see. And then remember, deductive reasoning is basically using rules or logic of like, hey, if this is the case, then this has to be the case as well. So, okay, here's one. If a student is late returning a library book, then he will be charged a $2 late fee. Bob returned his library book late, so he will be charged $2 late fee. What do you think this is an example of? And the answer is deductive. Why? Well, because it is based upon library's policies or rules or procedures. And so therefore it's deductive reasoning. Now, Andrea notices that every time she wears her favorite jersey, her team wins. Okay, she's noticed that. And so she's wearing a jersey. So she concludes that Olathe South will win. Well, what does that tell you? Well, she's looking at a sample data and saying, hey, I notice this happens. So she's basing it on a specific pattern of observation. So she's using inductive reasoning. Okay. All right. Look at the next one. Newton's first law of motion says body at rest. It will remain at rest unless acted on by an unbalanced force. Okay. So Elise watches a soccer ball roll across the field. What is she using? Well, she's using deductive reasoning. Why? It's principles. Okay. She's saying, if this is the case, if this is true, and then this is the result. Okay. And then I'm noticing there's movement. So therefore it must have been acted upon, excuse me, by facts or definitions, by rules, facts. The last one, okay, is saying Miss Jackson notices that her megabyte usage increases by 2,500 every month. So the question is this, okay, she's noticing this from a pattern of behavior. So what is the deal? It is inductive reasoning, okay? So when you look at your homework tonight, you're going to be applying inductive reasoning. You're going to be telling if something is deductive or inductive based on, is it a sampling where you're trying to make a conjecture based on your observations, or is it going to be based on rules rules, facts, or definitions. Okay. And then also you're going to be looking at a Venn diagram, trying to figure that out. And you're going to be talking about when they say, hey, it's false. you're going to try to come up with a counterexample to say, here's why, here's what I found to differ.